you do have to hold on and fasten your seat belts. I assume that the more people gets frightened by all this, the less of the audience is happening. But that's good. Basically, on the day when nobody comes in, I can just walk away. So I don't mind that. Okay. So today I will go through a skimpy little one page. Just this page. The upper part of this page is in front of you. And the only thing I'm going to show is that Lagrange equations, the Euler-Lagrange equations of motions, which you saw appearing yesterday, they hold in any coordinate systems. And again, this statement, at this stage, this statement looks like a pure mathematical statement which has nothing to do with anything. However, this is a very important statement because you may started to sort of feel the power of this Euler-Lagrange equations of motion, because apparently it applies to anything. But with this addition, that it not only applies for any part of physics, but it applies in any coordinate system, it will also mean that you can use this Euler-Lagrange set of equations to solve problems the way you have never imagined to do that. And this fact that it will apply in any coordinate system will allow you to solve problems much easier, but you have to see and wait what that means. You have to wait, and later on you will see what that means. So why would we want to prove anything like that? You know, the coordinate transformation. What does that have to do with anything? Turns out that when I started my graduate studies in the US, there was a conference at MIT, and we decided to go with a couple of my friends to this meeting at MIT because we heard that Steven Weinberg will be there, and it was this was happening in mid-90s, and Weinberg got the Nobel Prize in the 70s, so he was already a huge figure by then. And so we went to see Weinberg, and we were sitting through many of these talks, and it was terrible because we didn't understand anything, and we waited for Weinberg, and Weinberg gave a talk, and we didn't understand anything. So it was just terrible. However, there were a few things in Weinberg's talk which very much impressed me, and I still remember very clearly a few of his statements. And the first statement that he made is that modern physics is based on symmetries, and especially modern fundamental physics. In modern fundamental physics, the symmetries are extremely important. Basically, they are the blueprint of all physics, just like the DNA is the blueprint of all biology. And additionally, he said that by now, so that was mid-90s, we know that the only important symmetries in fundamental physics are space-time symmetries and gauge symmetries. And at that time, I didn't quite appreciated those statements. But by now, I fairly well understand what that means. See, the statement is very simple, because what happens is that in the quantum framework, you describe the state of the system with something that you call the wave function, which typically depends on coordinates, like space and time coordinates. And the only thing that you can change about this function, there are two things. The first is that you can change the argument. So you can change the space and time, and that, you know, you can do some space-time transformations like simple rotations or rotations in 4 dimensions, Lorentz transformations, or more general coordinate transformations, which act on this part, and that just changes your point of view of from which point of view you look at the system. And the only other thing that you can change in this is this function itself, and in quantum mechanics, in order to keep the probability interpretation of this, the only thing that you can change on psi is the phase of psi. And so these transformations, these are the space-time, of course, space-time transformations, general special relativistic or just simple rotations or shifts. And these, later on, you will see, these are gauge transformations. So basically, the fact that it's only space-time and gauge transformations are relevant to modern fundamental physics just simply because we describe modern fundamental physics in terms of not wave functions, but quantum fields. But the quantum fields work the same way as the wave function, so I could use the wave function to illustrate that. And so I'm going to talk about the coordinate system and coordinate transformations. But last time I just told you that in quantum mechanics, the wave function itself becomes the coordinate. So when we use the coordinate in the Lagrangian framework, of course the coordinate means just much more than just the space-time location of a point particle. And so what I'm trying to say is that the ordinary space-time coordinate transformations, of course you understand that those are coordinate transformations. Turns out that the gauge transformations can be viewed as coordinate transformations in the Hilbert space. So all important transformations under which modern fundamental physics is invariant can be looked at as coordinate transformation. So it all boils down to coordinate transformations. Everything is a coordinate transformation. All the relevant symmetries that we find in fundamental physics is related to invariance under some coordinate transformation. So that's why it's very essential to look at this coordinate transformation business. So again, you don't even have to understand anything of that blah blah. because if you just imagine a single particle in this room, which is again the point particle classical mechanics, this whole setup applies for that, so you can envision everything just based on that simple setup, and you can just use that that picture to help you to understand the somewhat abstract things that we are talking about here. So I think I said that. I will probably say that. Probably I will just say it now. So, for example, Newtonian dynamics gets stuck when it comes to general relativity, because Newton's equations, especially Newton's second law, is only valid in inertial systems, and the whole essence of general relativity is that you want to step out of inertial systems, and if your equations of motion break down, let's say in some non-inertial system, that means you cannot do general relativity in that framework that has those equations of motion. And here, for example, you will see that Lagrange equations hold in any coordinate system. That means they hold in a system which is connected to your inertial system by a completely general coordinate transformation. So you have the license of playing general relativity in this framework. So so that's a huge advantage. That's a huge advantage that you have this tool, this weapon in your hand, which you know it's not going to be backfire in the worst moment when a whole bunch of agent Smiths are going to attack you. So let's dive into the proof. Earlier we saw that you have this configuration system, configuration space. So the configuration space was just the simple collection of the coordinates that you use to describe the system. So it's a big vector. It can be just a simple 3 vector in case of an actual point particle in this actual room. But it can be any more complicated set of either 3 Cartesian vectors, or even wave function, or even a field. So, so you have this configuration space in which you have this, which is spanned by the appropriate coordinates, which are the best to describe the system. And turns out that you want to change these coordinates, and it's not as frightening as it looks there, because it's a completely arbitrary and abstract function. The new set of coordinates q, just the function of the old set of coordinates. Just think of moving from here to there. So basically you shift your coordinate system by 2 meters, or you rotate it, or as David kept teaching you, you boost it. So you do a Lorentz transformation on it. So it's just it can be an ordinary coordinate transformation that you are used to, going from Cartesian to cylindrical, or going from, in a more extreme case, from a inertial system to a rotating system. So this could be something very familiar that you might be familiar with, or it can be transformation in the multi-state Fock space in quantum mechanics, but in the general case, it can be described by this equation. You have a set of new coordinates, you call them Q, you have the set of old coordinates, you call them X, and they are connected. They have to be connected by a function which has an inverse. It's better to have an inverse because then the coordinate transformation is not proper. Then the function that connects the two set of coordinates is not really a function. So you assume that you have this invertible function, and in order to see what's the equation of motion in the new set of coordinates, you have to know how, the first thing you have to know how the derivatives of the coordinates are connected. So of course, this whole derivation is done in terms of classical point-like mechanics. So the evolution is happening in time, and so the derivative is with respect to time. So the time derivative of the new coordinate is of course just the total time derivative of the new coordinate is of course just the partial derivative of the coordinate with respect to the old coordinate times the time derivative of the old coordinate. And then finally, because there's an assumption on explicit time dependence of the new coordinate, why not? Then you have, in principle, you can have the last term, the explicit partial derivative of the new coordinate with respect to time. So this is not a surprise, because basically I was trying to push this just you know, how to take derivatives of functions which are functions of functions themselves. So so the x's are of course functions of times, because the old system was described by this coordinate and the coordinates, this x's, and then it evolved. So x's must have been function of time. So that's where all this comes from. So that's simple. We are going to use this because, remember, the Euler-Lagrange equations of motion contain the derivative of the coordinate. So we have to be able to deal with that. And here we just related the derivative of the coordinate to the new coordinate to the derivative of the old coordinate. And so now we can carry on sort of building up the equation of motion in the new set of coordinates. Because the coordinate transformation is invertible, the opposite is also true. So so the derivative of the old coordinate can be just simply expressed in terms of the derivative of the new coordinate by the exact same token, because there is a function which you can write the new coordinate x, the old coordinate x is equal to the old coordinate x as a function of the q's and t, and then you can take the derivative of that and you get the exact same thing that you got for q dot. So that's obvious if the transformation is invertible. So now you can start looking at so the Lagrangian in the new coordinates, of course, is going to be the function of the new coordinates and its derivatives. So so that Lagrangian, which is here. I'm just thinking what's the best way to say this. Okay, let's just leave it as he says it. As you remember, the Lagrangian was the function of the coordinates and the derivatives, and so now we can ask what's the DLDQ term, because if you remember, we had a DLDX term. So in the Euler-Lagrange equations of motion, there was a potential term. If you remember, it was essentially the potential which depended on the coordinates, and so this was the potential term on which the derivative with respect to coordinate didn't vanish. So you can express this derivative in terms of the derivative of the Lagrangian with respect to the old coordinates, because what you do here is really just taking the derivative of a function L, which is the function of these coordinates Q. So L is a function of X and X is a function of Q. So you are doing something similar that we were doing up here. In fact, the first term looks very similar. So you take the derivative of Lagrangian with respect to Q, which is the derivative of Lagrangian with respect to X, and then the derivative of X with respect to Q. So far so good. What you shouldn't miss from sight is that the Lagrangian depends on two things, on the coordinates and the derivatives of the coordinates. And we just showed up here that the derivatives of the coordinates are functions of Q. This functional dependence comes in here. So here is an object which must be the function of Q. Because if this is not function of Q, then like the X is a function of Q. So you take the derivative of that function, it still remains just function of Q. So because the X dot is the function of Q, so when you take the derivative here, there will be two terms. This first term, dl dx dx dq, but then you will have to take the dl dx dot, and then the derivative of the of x dot with respect to q. So you can do this second part in various different ways. For example, you can just use the equation above and take the derivative of 212 with respect to q, and then you will get this. And again, have to remember that the time derivatives and q derivatives commute, so it doesn't matter which one you do first. So once you convince yourself this is correct, and again the structure is very simple, you just take the derivative of Lagrangian with respect to what it depends on, namely x and x dot, and then you multiply those terms individually by derivative of with respect to q. You get this complicated looking thing, but that's fine. It's not so bad at the end, you will see. So in order to build the kinetic part of the Euler-Lagrange equation, then you do something similar for the derivative of the new coordinate. Because if you remember, the Euler-Lagrange equations have two terms. I call this the potential term because the potential in this conservative, under this conservative assumptions depends only on the coordinates, so only the potential part of the Lagrangian depends on the coordinates, so you can call this the potential term. And then the other term, the kinetic term, only depends on the derivative of the coordinate. Exactly because we define the kinetic energy as the quadratic form of the derivative of the coordinate. So so when you take the derivative with respect to the derivative of the coordinate, take the derivative of the Lagrangian with respect to the derivative of the coordinate. Essentially, this is the kinetic term which comes into play. So, so to build a kinetic term, we have to take this derivative, but that's easy because what this is really is the derivative of Lagrangian with respect to the old coordinate and derivative of the old coordinate. Sorry, derivative of the old coordinate, and it's too many derivatives. Taking the derivative of Lagrangian with respect to the derivative of the new coordinate is just the derivative of Lagrangian with respect to the derivative of the old coordinate, and multiplied by the derivative of the old coordinate with respect to the derivative of the new coordinate. It's way much more complicated to say this than just to look at those dots. So here, again, we have seen that there is only one term. There is only one term because the derivative. Why there's only one term? Yeah, because the Lagrangian. Where does the Lagrangian depend on Q dot? The Lagrangian depends on Q dot only where x, only through x dot. You see, x dot explicitly has the Q dot dependence, but x, if you look at x, where is x? So x is written here. X has no Q dot in it, so there is no derivative of Lagrangian with respect to x and x with respect to Q dot. So there is only one term. So at that stage, this at least is even simpler than that. However, we have to still take the derivative of this term with respect to time, because that's really the kinetic term in the Euler-Lagrange equation of motion, and so that goes as follows. First of all, he already simplifies this before he goes here. He already simplifies this equation, David Tong, crossing the derivatives of, but of course, okay, you don't necessarily encourage to do that. Yeah, just you can prove this equation properly or more properly by substituting the expression of Q dot, which we derived up here, and then putting it to the left-hand side here, and then what you get is essentially presumably the first term vanishes. I don't even see that how. So Q dot. No, sorry. The second term vanishes. Second term explicitly vanishes, and the first term just gives you this, because this derivative with respect to Q dot kills off this Q dot term, so it just makes it 1. And the prefactor, which is this, remains, and then this term has no Q dot dependence, so it just dies. And so so dx dot dq dot just gives you this prefactor, which is just dx dq. So so you can even simplify this term further. So the derivative of Lagrangian with respect to the derivative of the coordinate is dl dx dot, derivative with respect to the old coordinate, multiplied by this coordinate transformation. It's the something like the Jacobian of the coordinate transformation, dx dq. So then take the time derivative of that. take the time derivative of that. So everything depends on time. So you have these two terms multiplied into each other, but each of these depend on time. So you have to do the time derivative according to a chain rule. So you take the time derivative of the first term, and then you take the time derivative multiplied by the second term, and then you take the first term multiplied by the time derivative of the second term. And so the first term is obvious. The second term, you can see that the second term is that in various different ways. Again, you can take the q derivative of 212, which was up there somewhere, and then you get this. Again, time and q derivatives commute, so that helps. So at this stage, it looks bad. It looks very complicated. The whole thing doesn't seem to make any sense, because you have this potential term, and it's complicated enough. It gave you like 3 terms, and then you have the kinetic term, which at this point consists of under 3 terms. And then you can sum these up more precisely with the right sign. There's a negative sign between them, to form the Euler-Lagrange equation of motion, and sort of cross your fingers that you will get something reasonable looking. Amazingly, because of this particular structure that emerged here, namely this second term actually is the same in both of these expressions. This second term, which is the complicated term, just goes away. It just vanishes due to the negative sign. So what remains are these first terms, which are the simple-looking terms. And if you look closer, both of them have the Jacobian of the coordinate transformation, so that factors out. So it's right here. And what remains, amazingly, is an Euler-Lagrange set of equations for the old coordinate. So the kinetic and potential terms of the Euler-Lagrange equation written in the old coordinate. So after the dust settled, what you see is that the Euler-Lagrange equations in the new coordinates are equal to the Euler-Lagrange equations in the old coordinates multiplied by the Jacobian of the coordinate transformation. And this means the following. Because the Jacobian of the coordinate transformation cannot vanish. Because if it vanishes, the transformation is singular. So it's an improper coordinate transformation. If this prefactor vanishes, if this Euler-Lagrange set of equations vanishes for the old coordinates, which is the equation of motion for the old coordinates, so it vanishes, then the left-hand side is 0. In other words, you have an Euler-Lagrange equation, set of equations in the new coordinates, which looks exactly the same as the Euler-Lagrange equations in the old coordinates. So the Euler-Lagrange set of equations is invariant under an arbitrary coordinate transformation, as you see, as long as the transformation is invertible. So its Jacobian is not singular. And this is an amazing thing. This is an amazing thing because Newton's second law cannot do this for you. So we will see it on Monday and Tuesday in the tutorials that and you know this very well. You take a pendulum, you put it on the table, and then you swing it, and it goes back and forth. But if you leave it there for a long enough time, it starts to rotate, because it's in the crazy rotating system of the Earth, and so you take the Newton's second law, which is written in a apparently non-rotating system, and once you transform into a rotating system, then Newton's second law changes, because you will have these fictitious Coriola and centrifugal forces. And so you have to write those forces on the whichever side of Newton's second law, depending on whether you are in a inertial or rotating system. And so the you will see this on Monday, how the form of the equation of motion changes. However, in the case of the Euler-Lagrange, you don't have to worry about any of that. Namely, you just construct the Euler-Lagrange in this form, and it will always hold in this form. This is the reason why it can be used to do general relativity, for example. And this is the reason why it can be used in the quantum field theory setting, where you keep changing your gauge. And it's extremely useful, because, again, setting the right coordinates is essential to solve the problem. In earlier years, I used to do really wicked things with students, assigning electrodynamics problem, which is like a spherical problem, and ask them to solve the problem in Cartesian coordinates. And you know, it's just the worst thing you can imagine, because the coordinates just don't match the symmetry of the system. And sure, you can push through that, but you don't want to. And what this property of the Euler-Lagrange allows you is that you can go to the simplest coordinate system that is the most suitable for the problem. And then you are allowed to use your equation of motion in that set of coordinate system. It's guaranteed that it's going to work, unlike, for example, Newton's second law is going to break down in various cases. So that's a huge advantage again of this Lagrangian system, and we will make use of that. In fact, continuous use of that, because later on we are going to, in fact, very soon we are going to introduce what are called the generalized coordinates. And I know this is going to be, or it's potentially a confusing thing, because I already emphasized a lot how this coordinate, which I'm talking about, in the classical mechanical setup, can be thought as a much more general object as you go away from classical point-like mechanics. But just staying within point-like classical mechanics, the notion of the coordinate can be further generalized. We are going to do that, and we are going to introduce these generalized coordinates. And these generalized coordinates are not so foreign for you either, because you have seen various sort of standard coordinate systems, and you are used to the fact that you can transform from a Cartesian system to a cylindrical system. So you can do some trig, and then you can connect the two sets of coordinates. So you are familiar with various different types of coordinates. What you are not familiar with is that you can, and this is the sort of a bit of a shocking part, you can mix and match arbitrarily defined coordinates that suit the problem the best, and you can use them in the same problem. In other words, you don't have to stick to one of your sort of predefined coordinate systems when it comes to solving a classical mechanical problem in this framework, because you can set up your own coordinates. You can take an angular coordinate from what you knew a spherical coordinate system, and you can take an x coordinate from a Cartesian system, and you can assign them. You can write the Lagrangian in terms of those coordinates. And you know, in your usual coordinate systems, coordinates were better to be, or coordinate directions were better to be orthogonal and stuff like that. And you don't have to, there are no such rules anymore. Especially if you think about general relativity, which you don't necessarily appreciate at this point so much. But in general relativity, the coordinate axes cannot remain 90 degrees anymore, because the whole point is that you can take space. And if there was a, there is no traditional sponges anymore, but in general relativity you can take space and you can do these sort of things to space, and look at the coordinate axis. What happens with coordinate axis? They don't remain 90 degrees anymore. So in more complicated cases of physics, you abandon or you have to abandon your traditional coordinate systems and even coordinate notion. And we are going to do that in a couple of lectures. I will a little bit more properly introduce the generalized coordinate, but already early this week in tutorial and on Monday and Tuesday I will stress this, that there is always a set of coordinates in which the problem is easier to solve in. So on Monday or Tuesday I call this sort of the most appropriate coordinate, which in the case of the pendulum was this angle. Remember the theta angle, and so we will generalize that a little bit further. I will try to show you many different examples when we are going to construct a Lagrangian, and you can just simply forget about writing the Lagrangian in any predefined coordinate systems, as long as you picked your own suitable general coordinates. And the nice thing is that your Euler-Lagrange equation is going to work in those coordinates. As long as those coordinates are linearly independent, so you have this coordinate transformation, let's say a Cartesian, and your coordinate, your defined coordinates is invertible. But yeah, you have to develop a little bit of intuition, but the minimal amount of intuition. Not to pick very bad coordinates, but frankly, I have never seen that that would have been a problem, namely this condition. The people would have fallen into a trap by picking such a bad set of coordinates. So anyway, I think on one of the tutorials I will spend a little bit of time on, again, just within point particle mechanics, how to pick the most suitable coordinates for the problem, and then you can just construct the Lagrangian in that set of coordinates and stick it into the Euler-Lagrange equations and know that you are doing the right thing, because the Euler-Lagrange equations work in any coordinate system. So so that's it. I am done for this week. So I will see you on Monday.